So priority for us, it sounds like, is the two tests coming tomorrow. Yeah? So what do you know of the physics test for tomorrow? What to expect or what it's going to cover? Oh, three masses. Yeah, sure. Okay. Mm-hmm. Okay. 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 Sure. Okay. Sure. Okay. And? Nice. Awesome. Okay. Congrats. Good. I mean, you earned that. You put in the hard work. So that's good. Let's keep the ball rolling then. Okay. Oh wait, you can't see my board, eh? Let me share that. Okay. Can you see that okay? Okay. Oh, perfect. Okay, that's honestly so good because you know what to expect and what kind of questions to, like, what difficulty level and stuff like that. So, okay, awesome. Okay. Okay, okay, sure. Yeah, so it's like six questions inside of one. Sorry. Are you gonna steal Sharon? Okay. Sure. Yeah, no problem. Yeah, take your time. Perfect. Okay, no worries. Yep. Perfect. Okay. Okay. How did that feel? How did that sort of comparison feel from the first one, the second one? Kind of same sort of question. Similar-ish, at least, right? You feel better about those kind of comparisons now? Like even just seeing it multiple different times with like A, B, C, D in this one is helpful. Mm-hmm. And find the number out front. Yeah, exactly. Yep. Okay. Okay, yeah. Whatever way works, right? Okay. So Ceres is a dwarf planet located in the asteroid belt. Did you try that one? You have? Yeah. If you want to, we can try it together. Or I can kind of see you try it and guide you through it. What do you think? Okay, so let's take a look. Yeah? Okay, perfect. Okay, so close it down. Don't cheat. Here, I'll pull up my board now. We'll see if we can do it kind of, as if it was authentic, as if we saw it for the first time here. So, first thing that I just kind of want to ask you is like, how many questions do you think this, or how many questions? How many marks do you think this would be worth? Mm-hmm. Mm-hmm. Okay, the test. But let's say this question here, for example, if I was to sort of mark this, what would this be out of? Oh, I almost trying to write on it with a real pencil. Like I'd say like probably out of 4 or 5, right? Yeah? Okay. So something to kind of just keep in mind, okay, is sort of like how many points, where you're getting your points from, right? Probably a correct answer, probably proving your correct answer, probably bringing together a key relationship, something like that, right? Okay, so I want to sort of just give you some time here. How about I give you like 6-ish minutes? See how far you get, okay? How do you feel about it? And if you ever get snagged, so like I want you to sort of always feel like you have a good momentum and you sort of always have a thread to follow, always have a crumb trail to follow of like, okay, now I see where to go, now I see where to go. If you don't feel that, then I want you to tell me, okay? If you feel like, wait, what? If you feel that feeling for more than, let's say, 10 seconds, okay? Okay. Okay, 6 minutes timer started now. No, let's just start for A. Let's just start for A. I'll see how far we can get. Okay. I want you to tell me if you ever get caught up. So what I'm going to do here, actually, I'm going to send you the question as well in the chat so that you can look at just the question. Then what I'll maybe even do is on my board, I'll kind of like solve it after a few minutes and see if we can arrive at similar answers. Okay. Okay. So I'll give you a few minutes here and then I'll jump in as well. Okay. I should be right back. I'm just going to grab some more water. Okay, cruising along. Still have a crumb, still have a thread. I like it. That's good. Okay, so I'm going to kind of pause my sharing and we'll see if we arrive at a similar sort of thing, okay? Okay. I'm not sure if you're talking because you're muted. Oh, okay. Okay, sorry. No worries. I know how it is. I got 3 siblings too. Okay, there you go. What do you have? A brother, older or younger? Mm. Mm. Nice. Mm-hmm. Well, what is the, like in the FG equation, right? It's a big G, which is a constant, and then there's a big M, and then there's a little m, and then there's an R squared, right? What is the big G? It's a constant. Does it depend on the circumstance that you're in, the mass that you're talking about, the planet you're on, the how big the planet is? Does G depend on that? No, it's just a constant. It's just a number, right? Okay, what about big M? What is big M? Oh, you can't see my board, sorry. Uh, okay, can you see that okay? So just in that equation there, right? Big M. What does big M represent? Uh-huh. Have you seen it represented? It's mass 1. Yeah, what does mass 1 mean? The first mass. Good. Okay. Okay. What is the first mass in our story? Another way to say this is, what is the first object that has mass that we're talking about, that we're going to care about? What do we call the... Sure, sure. Okay, so M1, let's say. So, oh, okay, what are you using? Okay, yes. So like this. Right. Okay, good, good. But what is this one mass? Okay, so that's the problem. So what is the Earth's G value? What is the Earth's G value? Good. On the Earth, it's 9.81 meters per second squared down, right? Or like towards the center, right? Okay, and that's why it's a vector. Where does that come from on this equation? It's g, which is just a number. Doesn't matter what's happening in the actual problem, so let's move on. M, what's the m that we're talking about for this 9.81? The mass of the Earth. That is the thing that you're on that is going to cause the gravity. Cause the gravity, not the thing that is going to experience the gravity, right? So for us, the hammer is the thing that's going to experience the gravity. Okay, this isn't really the best way to think of it, but it's a literal way. It's a good kind of way to think of it in practice. But in terms of physics, they both feel the same force on each other. They're both pulling on each other, right? But one of them is way bigger than the other, so that one gets affected a lot more, right? So the Earth pulls on the hammer just as much as the hammer pulls on the Earth, but we really only see the hammer move. We don't see the Earth move, right? That's all I'm trying to say. That's all I'm trying to say, okay? But here, it's depending on the mass that's causing the gravity. The mass that's causing the gravity. Is the hammer the one that's causing the gravity? No. So, in fact, we don't have enough information to get there. We don't actually need to find the mass. Because what do they ask us for? The gravitational field strength. Which is going to come out as a acceleration in some sense, right? Can you figure out what the acceleration of this hammer is? Yeah. No. Right? Yeah, that I agree with you, right? The mass of the object has to be the same as the radius of the object that you're on. Object meaning planet, right? You're only really going to use this for a planet, okay? Okay. So then there must be another way to get to acceleration. What other, so this is question right now for me is failing to the fact that I didn't get a givens table. What sort of things were you given? Did you write down everything you were given? What were you given? Yeah. Yeah. Sure. Sure. Okay, so what should I write that as? Delta T of the hammer is 3 seconds. Okay. How can, I put that as kg. It's 1.5 meters. Okay. So we kind of tried our best with the first equation, with kind of what we might think is the equation we're supposed to use to calculate the gravitational constant, right? But we were given other values. We were given heights and times. Does acceleration factor into that story? Heights and times somehow? How are those related? Heights and times, how are those related to acceleration? Heights and times. Heights and times. Distances and times. Oh, yeah, sort of. You're maybe forgetting your last unit. You had 5 friends. 5 friends to help you. Your 5 equations. Right? Maybe that one. Or maybe another one that you could use to solve for the acceleration. Really, what we're trying to do is solve for the acceleration. We're trying to figure out what is the gravitational acceleration. Because if this question was happening on Earth, that A value would be our G value, our 9.81, right? So this problem has a weirder distance and time and initial velocity because it has a different acceleration. And we can solve for that acceleration with these values that we know, right? Good. Let's get a drawing of this hammer story. So what I would do is I would be getting a drawing of my kind of planet going. That was my initial impression, right? And that's kind of like the radius. And my question is like, what's the mass? That was my impression too, that we were going to be using that equation, right? But it turns out we couldn't. So now let's draw the hammer situation. So now we have a hammer that's from 1.25 meters above. We're going to drop the hammer. Not bad. Got terrible at the end there, but that's okay. We're going to drop the hammer, and it's going to take 3 seconds, right? Okay. So, do we know enough? What are the 5 variables that I was talking about? 5 friends? What are they? Uh-oh. Has it been that long already? It's only been 2 weeks. You forget it so fast, eh, when you have to switch totally. I'll search you off one. V1. Yes. 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 Beautiful. So we want to solve for this one. We're trying to solve for the sort of planet's G value, right? And so what do we need? We need 3 of the others to solve for the 4th. What do we have? What is it? You just made a choice. Be careful. What choice did you make? You're right, as long as you agree with this choice that we made. What did you make? What choice did you make? A choice. A choice that comes to every physicist when they come to one of these problems. Which way is up? Which way are you looking? Which way is positive? You just made 1.5 down positive. So we got to be careful there, right? So it's okay to make that choice. Just be aware that when you do make that choice, right? Okay, so we're going to say down is positive for this question. Okay, so then 1.25 meters. Sure, I'm with you. What else do we know? Good. Do we have to say positive, negative? No. Get out of here with that. Okay, what else? Like we must know one of those 2 velocities, right? If we're going to be able. Why? No, you don't even have to finish your sentence. Because you are boom dropping. As soon as you say drops in physics is that's a huge like point. That's a huge valid reasoning or something that matters. Drops means V1 is going to be 0. I'm going to just let it go from rest. And acceleration is gravity. I'm just going to let gravity do its thing, right? So that's a loaded word in physics, drops, okay? But that's the word you would point to say that's how I know velocity 1 is 0, right? What if I said, oh, it hits the ground, velocity 2 is 0? What would you say to me? Isn't that true? It hits the ground. It's sitting there, right? It's sitting there, not doing anything. The velocity is 0. It's already hit the ground. That's a huge but. I wouldn't even give them the yeah. I would say no but. I mean, yeah, okay, yeah, I'm with you on that one. But sometimes it asks me about, the ball on the ground or whatever. Why don't I take it as like there's an easier discount that you could say to this person that does this mistake. This is a common mistake, something that you've probably done yourself. It's assuming that the crash of hitting the ground and then tumbling and bouncing and falling and all those changes in velocity and all those different accelerations, one initially is straight upwards and then it might hit something again and go sideways or whatever, those are all different types of acceleration. What we're doing is we're talking about one time segment that has the same acceleration throughout that time segment, right? So we have to catch this thing right before it hits the ground, because as soon as it hits the ground, that's a new acceleration segment. So we're not allowed to kind of put those in the same basket. We now have to separate those two sections. It's sort of like having a graph that's like part of the graph is a triangle and part of the graph is a rectangle, and you're trying to sort of pretend like the whole thing is a triangle or pretend like the whole thing is a rectangle. Right? It doesn't. You have to split it up. You can't use either formula for either one. But if you use them separately and then combine them, then you're fine. That's the same thing for us. So if we accidentally include a little square in there, that's the equivalent of adding in an extra segment that has a different acceleration than what we're saying it is, which is the gravity, right? So the gravity wouldn't have caused this thing to have a v2 of 0. Gravity was causing it to speed up downwards, right? So to say that that's because of gravity that it hits the ground and now has a velocity of 0, no. This thing is only going to speed it up on the way down, right? Okay, cool. So that's your answer to that question that makes that person that makes a mistake. Okay, awesome. I love this. You caught it. It drops. So then velocity 1 is 0. So now we have 3 of the 4. And so now we have to figure out just which formula we should use. So we want to include V1, delta T, A, and delta D. So we'll do that one there. Does that make sense? And then we solve for A. For sure. Yeah, that's going to be a physics skill moving on. Like, more and more, we're going to slowly not give you the most direct way to get there. And we're going to give you these sly ways because now you're more capable, right? Like, before, if we had sort of introduced an idea, we wouldn't have been able to, like, give you some other information that would have led to the same place. But now you have more and more skills, which means you can kind of get places in the physics world, right? So, and pretty soon, you're going to be able to turn this question into an energy question. And so I could give you enough information, and in fact, we can turn it into an energy question. Yeah, they have everything. Yeah, exactly. Yeah. Yeah. Okay, so what's nice is that the energy is the easiest way to look at everything. So if you see all of these things, like for example, in this question, I would have taken the energy approach right away because it would have gotten us the same answer, okay? If it doesn't, then we go to kinematics, then we go to dynamics, then we go to some of that harder stuff. Energy is like super easy. So when you start to see dynamics and kinematics in the same question, energy, like that's a clue, right? Like you probably won't be there for 45 minutes trying to do 6 free body diagrams. It's probably just an energy question, right? Those are really strong clues. Okay. So I want to change your feelings a little bit about that, but I know exactly kind of what you're referencing. So, and we can talk about it kind of when we get there. But yeah, I think I'll change your perspective just a little bit on that. I'll tweak it a little bit, hopefully. So we can calculate. So do you kind of agree with me that this is solvable now, that we can solve for the acceleration and that because it's dropping, its acceleration is entirely due to the gravity on that planet, right? Do you agree? Okay. Okay, so then how would we calculate the mass then? Yeah. How do we go about calculating the mass? Yes. Yeah. Like what we were trying to do last time was use m to solve for g, right? That was like two unknowns in that equation. Well, now we have one of the unknowns, so we can actually use that equation and solve for the m, right? Good. Awesome. With the two masses. What do you mean by that? Would it matter? Well, you would have to use, you can't use gravitational field strength. You have to use Fg, right? Because then that's Fg, right? That's G m1 m2 times r, right? That is uh, that is the force of gravity. That is Fg. That's not just G, right? So we would have to do some sort of calculation of mg because we only have G right now, right? Like this would have gotten us G. So let's say, for example, we solved that G was, well, let's take a look. Like 1.5 meters, 3 seconds. That's a long time to fall on Earth. That's a slow fall, right? Do you agree? Okay, so then G is probably something like, give me a guess. Reasonable guess. Something that I couldn't say it's no. So say, for example, if you said to me -4, I'd say, no, get out of here, right? Sure, yeah, yeah. If you said to me 12, I'd say, no, get out of here, right? Why? Yes, good. Good, yes. Sure, absolutely, yeah, sure. Okay, so let's say 3. Just nice number, okay? 2, sometimes I just don't like it because the squared of 2 is the same as 2 times 2. So that's why I just don't like using 2 as an example number, okay? Because 3 squared is a lot different from 3 times 2, right? Okay, so let's say G was 3, right? If what you want to do, so first of all, let's just agree that we already have a pathway there, right? We already agree that we could kind of plug this in for this G here, right? Well, that is what we just solved for, right? So if we had that G value, then we could plug it in here. That is a constant. That is what we're solving for. That is, do we have it? Okay, so then we can solve for m, right? Do you agree? Okay, so that's one way we could do it, yeah? Another way we could do it, and remember that the difference in the two formulas, it's very, very close. It's just that all we've done now is we've sort of said mg, and we've turned this into a force. Well, the only difference between these two is it's been multiplied by an m. Well, that's the same thing here. It's been multiplied by an m, right? Exactly. That's why we don't do that. Yeah. Yeah. And which m would that be, the one canceling out? Would that be the mass of the planet, or would that be the mass of the hammer? It better be, right? Or because you don't want your mass of the planet to cancel out. You already know the mass of the hammer, right? Okay, good. They're so similar. Okay, so this is where analyzing the unit can really, really, really help you. okay? Analyzing the unit. So this should be in what unit? What unit should this be in? What dimension? Should it be seconds? Should it be meters? Should it be kilograms? Should it be meters per second? What should it be? What is our g? What is the value of our g on Earth here? Yes, seconds squared. This is an acceleration, right? Okay. What we do here is we multiply g by m, and we get, what's mg equal to? Yeah. So the force of gravity is measured in newtons. And that's going to be kilograms times meters per second. That's what a newton actually is. That's like, we say newtons instead of having to say kilograms times meters per second squared every time. Okay? Yes. On this side, if we're going to multiply this by m, then we have to multiply this by m, right? Those green m's are the same m. They're the mass of the object on the planet, right? This g value is entirely a quality of the planet and the surface, you know, being at the surface of the planet. Do you agree? Okay. Let me ask you this. Do you need two masses in order to tell me what the gravity is on a planet? What's the mass, what's the gravity on Earth? Why? What's the gravity on Earth? Yeah, because you can tell me that, and I'm only giving you one object on Earth, right? Okay, so the big question is, are there one mass or two masses? The mass of the planet that you're on will always be there. It's in there in both equations, right? The only difference is, do you have a second mass where you're looking at a particular value, or are you talking about the planet in general? If you're talking about the planet in general, you're talking about this g value, right? If you're talking about a particular object and what it's experiencing, then you're talking about fg, right? And you might have both masses that matter. Does that help a little bit? Like, this g value only cares about the planet. It doesn't care about kind of like what's on the planet, experiencing that planet's gravity, right? Because that comes when you multiply both sides by m. That makes sense? Mm-hmm. Yeah. Ah, okay, yes. Okay, yes. So you'll notice, like, in this equation, like, you spotted it well. So, like, let's not say that you're not good at spotting it, because you spotted this well. That, wait, I'm not going to use the mass of the hammer and the radius of the planet. That makes no sense. Something's wrong here. Like, this doesn't work. To spot that you didn't have enough information, that's already, like, some knowledge. That was good, okay? The thing that sort of, like, is the crumb to follow, right, is the fact that A, you don't have enough information to the way that you want to solve it, simplest way to solve it, like most direct way to solve it, you don't have enough information. The other thing is that, like, you have times, dropping, distances, like that should scream out to you your 5 equations, right? And if you have a good understanding of this g value being really strongly associated with acceleration, right? And the acceleration that you experience on a particular planet, that's what this g value is, right? The gravitational field strength. Then, you know, that connection, I think it can be a little bit stronger. But I think even if you were to see another question now, do you feel that like if you were to sort of like be a little bit at a dead end and then saw some kinematic stuff, you might say, oh, okay, let me try to get to g that way? Do you feel like that lesson has been sort of cemented a little bit? It's tough to say, obviously. Hmm. For sure. Yeah. Okay. Mm. I don't need them though. All right. Okay. Sorry. Yeah, I that's like that's why you have to sort of like put an order to the things that you want to like where you want to go, right? You don't want to just say like, "Oh, there's a distance. Let me go into like the five equations." Like it could be a simple velocity, time, distance question or something, right? You don't want to jump into like something that fits. You want to jump into the simplest thing that kind of fits the best. Your job is to kind of like put those two things together, right? Like okay, this would probably fit the best, but it's not the simplest, or this is pretty simple, but it probably doesn't fit. Those are neither are good, right? But this is simple and this kind of fits. That's what we tried with this, right? And it didn't work, so that's why we tried a slightly more complex one, right? So yeah, like that's kind of like a skill that it seems like you are developing as we go here. But of course, you have to kind of develop this across each unit and across each section, right? Like get to know questions. So that's a big part of physics. Such a big part is just like, oh, I've seen a question like this. Okay, I know what to do, right? Like that feeling on a test is a game changer. I'm sure you felt that, right? Where it's like, oh, I recognize this type of question. Let's go, right? Oh, okay. Okay, so I want to change your feelings on that too because part of that is confidence, right? Okay. But part of going into a test, especially like kind of like mentally going into a test, is that you've seen every difficulty, particularly a difficulty of type of question that you're going to see, right? You kind of know what's off limits and what's on limits. And then from there, like being ready for anything is where I want to get to, where you're sort of like throw your craziest question at me as long as you don't break, as long as I don't need to use calculus or as long as I don't need to use like chemistry or something that like we haven't been talking about, then I can solve it, right? Like that's where I want to get you, right? Obviously that's like, a tough feeling to like have going into a test, but obviously like, you definitely have I think more ability, more natural ability, but also more hard worked in ability, then you give credit to yourself. Like you sort of, more than a few times, just sort of like, I don't know, I think it might be this, and it's the right answer. It's perfect, right? So part of this is also just a mental game of kind of like, being confident to take a reasonable guess, right? Okay, so determine the gravitational field strength at Ceres at an altitude of 150 above its surface. So let's just kind of talk about what you would do there. What would you do there? Hmm. Okay, so let's say with a gravity of 3, and the radius, okay, so that's a lot smaller than Earth, so it's kind of becomes tough now to compare the mass and the whatever, right? If it was the same radius of Earth, then we would have been able to say it weighs a lot less, right? Because its gravity is less. But I'll just kind of give you a mass here, okay? So, not in highlighter, but let's say that we solve this to be, um, oh, okay, beautiful. Yeah, no worries. No. uh, it only happens at like the worst times too, eh? What's going on? You gotta adjust the settings on that. Like the actual what your address was? Yeah. Oh, okay. So right, that's gotta be tough. Yeah. You got it? Okay, so give me a mass here. Massive series, so B. The answer to B. 0.27. Okay. Kind of big. Okay. So, yeah. So, okay. So then what do we do? So let's try to solve C, kind of now having solved B. Do you want to try to just clean slate, try to solve C here? C. Yeah. Okay. Take it onto your page. Yeah, yeah. You're good enough now where you can sort of tell like, okay, I'll be able to solve this, or wait, no, I won't be able to solve this, right? So, yeah. Okay, I'm just gonna run to the bathroom. I'll be right back. Okay. Sorry about that. How are we feeling? Oh no. Okay. Okay, awesome. So, big question. Big question, okay? I caught a sniff of this when we were approaching this question. It's kind of what I wanted to give you a chance to do it. Big question is, did you check your units? Did you use 150 or did you use 150,000? Did you use 150 or did you add 150 or did you add 150,000? Why? Yeah! That's great. That's awesome. That's perfect. That's all. That's like the biggest thing. Honestly, like that's what this whole question was about. Okay, like there was one thing which was like, did you know what to do here? You add it to the R value, right, and then you square it. Hopefully you didn't add it after squaring. Is that right? You added it before squaring, right? Okay, so I trust that you got the right answer here then, right? And so that. What did you get? 0.161. Okay, so let's ration it out. First of all, should it be greater or lesser? Why? Wait a second. Whoa. Determine the gravitational field strength at an altitude. Does the field strength care about what object is experiencing the field strength? Is it one object dependent or two object dependent? This G value. And what is that one object? The planet. Good. Yes. So you use G, M, which was the M that we found, right? And then did you divide by a bigger number or divide by a smaller number? Was the number in the denominator getting bigger or was the number in the denominator getting smaller? The number in the denominator. Even just check my screen out. Here. Did this value go up? Sorry, can you see? No. Did M go up? Did the mass of the planet go up? Yeah. You're like that's a good reaction to be like, "Wait, what do you know? What are you talking about? The mass of the planet just stay the same, right?" Yes. What changed though? Why did G change? In this equation. Just the purple, right? I'm just looking at the purple, sorry. What changed in this equation that caused G to change? Wait a second. Can I just see what you did here? I think this is totally my phrasing because you got the right answer here, okay? And part of what I'm trying to do here is build this confidence in your understanding that, oh, yep, that makes sense. I feel confident in that, okay? Good. Okay, awesome. That's what yeah, exactly, right? Beautiful. So the denominator got bigger. Okay, what happens to numbers when the denominator gets bigger? They get smaller. So is it reasonable that the value got smaller? Like now we've kind of pointed at every single thing and have said, now does this thing that we've pointed at now connect? Like what we really would have done is thought through the thing that we just described, this little thing that we just described, which is that, like, oh yeah, I was adding to the denominator, so that makes sense, the number gets smaller, right? That's what I mean to say. That's why that makes sense, that the number gets smaller. Are you confident in that now? Okay. Sorry if I was kind of doing a little bit of a poor job there. But okay, cool. So, and also that's a pretty significant drop. Like that's like almost half, right? Which makes sense because 150 kilometers, this is only 470 kilometers, right? Or is this 47 kilometers, right? Like, I don't even, this, I would have to convert it. Let me think here. This is what? Yeah, this is 476,000. Okay. So every three is 1,000. So that means this is like, minus three, that's 1,000, and then there's two left. So now you're in the sort of like hundreds of thousands. Okay. Okay, so yeah, makes sense, right? That we're kind of like adding quite a bit of distance. Okay, all of that is to sort of like make sense of what you've looked at. Let's look at another, maybe an orbital problem, and then something I just want to check in on. How is the math? Where are you? Like, is physics definitely the one that we should be focusing on? Do you feel good about math tomorrow? Okay. Okay. So let's build some. Yeah. Okay. So let's build some more sort of confidence there. Do you think that we need to sort of do this a little bit, like do the actual in the trenches work of like solving line to line math stuff of physics then? Like, how do you feel about doing that stuff? Are you okay with me sort of saying, like, and then you could solve for A and this would be the value? Or do you want to do a bit of those lines? Okay. But do you, yeah. Yeah, like what I'm asking is, if I was to give you a problem like this, would you feel confident in like rearranging, subbing in, rearranging, and doing all of that, like whatever you had to do to solve for a value that was like left over as the only variable? Do you feel confident in kind of doing that math side of things? Like just the fact that you're saying you feel confident with the math test tomorrow means I think the math of physics is not that hard, really, right? It's rearranging for one value once you have everything in one equation, right? That's what I'm sort of asking. Okay. Cool. Yeah. Okay. I just wanted to check in that it's okay that I say, like, okay, now this is solvable, and you would get something like this, right? Like, instead of actually sort of spending the time there, because that can sometimes be a time sucker, and we can spend our time at other places. Okay. Okay, please do. Yeah. Okay, awesome. So let's jump to then another problem. Maybe another question type. Like, you feel okay with this problem then? We sort of like cruise through that one after a while there. So, okay, let's tackle it. Let's do it. hmm You mean like AP, like the coursework AP level? That's what you mean by AP? Okay, yeah, yeah. Okay, so I can give you one if you want. Okay, so let's numbers. Oh, that might mean that we need to try those ones then. Because that, like, our strengths are our strengths, right? If we keep focusing on our strengths, we'll never get better with our weaknesses, right? Like, you'll always, you'll be okay. You're going to be okay with your strengths. We should focus on the weaknesses to shore up everything. Okay, so, okay, let's see. Uh, oh. Oh, okay. Corners of a square. Okay. Okay, yeah. This is a little different than the one I was going to do. Okay, cool. Let's do it. Yeah, I think we could tackle these. Okay. So, let me sort of like what's nice is that it kind of doesn't matter what's where. What you'll do is the same, right? And it's really, really important that we just sort of always only ever have two masses in our mind at a time. We could, take a zoom out and not really be doing the physics with two at a time and then consider three or five or 10 or whatever. But at any one time, we will only ever look at two masses involved in a FG on each other, right? So that's important. That it's the same force on each other. Oh gosh, yeah. I forgot you're sharing. So it steals it from me. Okay, so do you want to zoom, or can you send me this document actually? Is this a PDF that you can send me? Or I could just grab a picture of it. Yeah, I can just grab a screenshot. Just zoom out for a second. I can just grab it here and then I can put it right on my board. Okay. Yeah. That if it works, then that works. But hmm, no, it is progressing. There we go. Okay, cool. So we did, yeah, we worked through this one, and then let's kind of, I'll grab the next like chunk of questions here if you want to even just scroll down. Mm, yeah, maybe there. There you go. Perfect. Yeah, Skype, you should be able to, like on the bottom on our chat, there's like a little like file next to a sort of picture window portrait thing. Oh, nice. Yeah, there you go. Okay, cool. Yeah, I can just grab the question from it. Awesome. Okay, so, um, okay, yeah. So the numbers, it's like I like the idea to kind of be able to follow it. So let's kind of do the same. Let's like, like it's a, yeah, but the general form without numbers. Yeah. Okay. Yeah. Well, let's be ready for something. Yeah, like we'll be able to do this with numbers for sure if we can do it without numbers, right? And like we may get it without numbers. So let's try it, okay? So okay. So, let's try this. Well, let's do this. Make it somewhat nice maybe. Okay? So, first, the first thing I want you to do is tell me where you think the most like where you think the leftmost mass is going to be pulled. The leftmost mass. So let's call this, we can call this one A, B, and C. Okay? So A, the mass of A is just M. The mass of B is 3 times that value. And the mass of C is 6 times that value. Okay? What is an approximation, including direction? I want to hear direction. And what is its unit going to be? What is this thing? FG. Yeah. It's the what from gravity. Why? Love it. Love it. Yes, good. Okay, that's huge. Right? And so is C, and that's what matters. Good. But B isn't tiny, right? It's not tiny. So it's not, I wouldn't say, like, would you say that it's going straight down? No. Good. Okay. Would you say that it's going straight at C? To the sort of above that or below that? What would you say? Straight at C. As if B isn't there? Whoa, wait a second, wait a second. Let's take a second. You and I and everything in the room around you and everyone around you and every little object that has mass is feeling gravity relative, right? We have to say that. That's what we're examining here is only three of them. Why don't we feel it? Why haven't we talked about this before? Why haven't anybody noticed this? They're tiny. Like force of gravity is a tiny force when you're talking about masses our size, right? But we feel the force of gravity to things like planets, right? Okay, but these objects, they don't have a planet. All they have is each other. So is A going to feel B? Yes. Which direction will their gravity be towards? That force. So there's FAB from A to B, and then there's FAC. Is there a B and a C force? There is. Okay. What I just asked about, okay, so let me sort of like bring this down to the world around us here, just nice and simple. This is something that our brain does nice and easily, is like when things are familiar, then it can think about more complex things. My coffee cup, okay? Me and the coffee cup have a force of gravity with each other, right? That relationship is entirely determined by our two masses, and there are radius between each other, right? Does any other thing in the universe matter? No. I have a cup of water as well. These two things, they have their own force of gravity and their own radius, right? Does that change my relationship with the coffee cup? What they do? No. It might change this thing's motion and which way it's pulled, right? And that might eventually affect me and this thing's relationship. But at any one moment, all you need is my mass, its mass, and the radius between us, right? So, what that means is I don't care. There is, in fact, an FBC that you asked about. There is one. Good question. But it's not relevant. What you're asking about is the cup. Hey, what about the cup? I'm talking about me and the coffee, and you're asking about the glass cup, right? I'm saying, nope, it's just me and the coffee cup. Okay? So, okay. What do you, well, let's, it's asking for the net force. So you're now feeling, this is like two things pulling on you, right? Which direction do you move? Usually your motion is because of an acceleration in that direction, which is from your F net in that direction, right? So if I have somebody strong pulling me on my right and somebody weak pulling me on my left, I'm going to go to the right a little bit, right? At least. Good. So, and the directions are not perfectly like left, right. What do the directions look like? That's what I'm asking is, what does this vector look like? And what does this vector look like? Those are vectors. We can draw them. That's exactly it, because I'm asking about the FG that this thing feels. So I don't care about B and C because it's not involved in the gravity. Like, in this cup analogy, you were talking about the cup and here, and I was asking about my gravity. Well, I am only going to feel the gravity from this thing, right? And I'm also going to feel the gravity from the cup, but then the coffee's not going to matter, right? So you can do them totally independently, right? This is what I meant by we're going to develop a system that I can add 30 things now, right? I have a paperclip here. I was also the whole time experiencing a force of gravity with this thing. Now the two cups don't matter, right? So that's the beautiful thing is you can add 7 of these things and it doesn't matter, okay? Okay, so let's get down to the equations. What do the equations look like? And, I do want to draw them, but for now, what do the equations look like? For FGAB and FGAC. Big G. Yeah. Good. Beautiful. Beautiful. Oh, sorry. In my drawing, I don't have it. This is L, and this is L. Right? Yeah. Okay. Yeah. Double check. Confident in that? Something's missing. Ah, yes. Good. Nice. Okay. Beautiful. Let's go. So, we have now a 3, an m squared, a g. What do we do with the top there? Ooh, wait a second. Wait a second. Which one of these is it? There's like many versions, right? It's not addition. Okay. The second one. Is the third one okay? Yeah, good, good. Yes, good. So, do the brackets really do anything then? No. The brackets are sometimes a way that I could do this without having to draw dots. But sometimes if there's a square there, then it's of course not the same, right? Usually brackets are there to sort of like hold a order of operations, but here we don't need it, right? Okay, so really I should have like sort of written it like this, but that's what we're doing, right? We're not doing 4m, so it's really what? Beautiful. And it's G out front of that. right? Good. Are you okay if I write the 3 out front? Why would I do that? Yes. Yeah. Wait, okay, wait. What I need you to do? You already told me this. You told me this answer a second ago. So I need you to zoom out. Remember what we're doing in this question, right? Is we're dealing with the general form of M. So our job is really just going to be to compare or find the original, right? Like that was a skill that you're now going to need to use, right? Okay, awesome. So let's do it for AC. Do you want to take it from here? Do you feel confident kind of like taking it from here for all of them? Or at least for the other one? Yeah. Ah, nice. Good catch, right? This isn't some sort of mystery triangle that has some sort of same length, all three of them, right? This isn't an isosceles or a equilateral triangle, right? So, okay, so then what do we have to do? I'll tell you this, it ends up being prettier than, you might think. Okay? You're thinking, oh, it's going to be messy. Ends up being nicer than you think. Yes. You said hypotenuse, right? That only applies to. All right. That's okay. What does that mean? What? Like, you don't have an angle. But don't forget about your other tool, your strongest tool. Greek guy, old Greek guy. Old Greek guy that contributed to math. Come on. Oh, like if you ask somebody on the street, give me an old Greek guy that contributed to math. Who would it be? Yeah, probably one of the famous. Not new, not Einstein. Old Greek guy. Just doing simple things like squares and triangles. He was concerned with triangles, this guy. Yeah. Oh, came up with a theorem. Old Greek guy. Yeah, Pythagoras. We have two sides of a right angle triangle. We can find the hypotenuse length. And that's okay, that's okay. So part of what I wanted to do with like dragging that out, making that weird, talking about an old Greek guy, that's how you remember next time, okay? As weird as it sounds, with our memory, if we have some experience that sort of like, is something to remember at least, you can do some association with a math equation or this sort of circumstance, okay? So in this sort of circumstance, what's that? Five friends. There you go. Exactly. Now you're looking for five variables, right? So that's another way to think of it, right? Like it's ringy. It rings a bell. It's just like our brains. Memory champions use stories to remember. Like, have you ever seen it? They can remember like a whole deck of cards in like a minute. Like as fast as you can run through it, they can remember the order that it came in, and they do that by just like telling a story in their brain, and it's totally story oriented, our memory. So if you can associate something that you're learning with like something that something that you are familiar with, or a story that happened, or some sort of memory that you already have, or that you can easily build, something like that we're doing, five friends, all that stuff, it's way easier, right? As weird as it sounds, or as maybe bad as it sounds, and I'm not going to give you any, but doing inappropriate, using swear words and stuff in mnemonics helps with this a lot because it's funny, okay? Or it's something that's like inappropriate that like your mind just like remembers those things way easier. So like I'm of course not going to recommend any, but that is like totally a good trick for trying to like remember like you have to remember I always the kingdoms, all of those ones, right? Like kingdoms, genus, species, like you remember in biology, all that thing. Like there was like a King Arthur one or something, or like there was like they like tell these weird stories like King Arthur went up a hill and ate a bread or something, and it's like how am I supposed to remember that? If you make it like funny or memorable or use a swear word, that's way easier. Okay, you'll come across a lot of that stuff as you go into university. You have to remember like people will be like, just remember these three letters, and you have 28 of them that you have to remember going into the thing. It's not so easy, right? Okay, so anyway, sorry, back to this. We're comparing to the original, right? So now when we sort of like, this the roadblock there was like, wait, what am I going to use for r squared, right? Now we know we are there, the radius between them, which is really the distance between them, is what? Now we got to do the math. If what is the old Greek guy's theory? Yes, good. See, that's one of those things that's like drilled into your mind, right? Like as soon as you said a squared there, your brain just like filled in the rest so easily, right? So start there, right? Like that's a good that's called an anchor. That's called a memory anchor. Okay, so start there now and now rearrange what you have. So what is A in this scenario? Beautiful. What is B in this scenario? Also L. And what is C in this scenario? Well, we don't have a label, so let's maybe just call it C and we'll say that's what we were looking for, right? And it's C squared. Okay, we'll come to that. What does this side look like? L, well, what does it simplify to be? Does it get any simpler? Ooh, wait a second. X squared plus X squared, your old friends, do they do this? Yeah, what would it be if it was X squared plus X squared? Awesome. Okay, all I did there, I used your old friends, right? That's an example of what I'm talking about. Simplify, make it something that you're comfortable with. Your brain can sort of like see what's different, see what's new, right? Another example of this is like use numbers, right? If I had plugged in a number there, we would have been able to prove that that was something was up there. Okay, so then this is 2. Beautiful. Okay. So then what is C equal to? 2L? Oh, sorry. I didn't hear it. Sorry. Okay, you feel good about that? What do you mean them both? Square root the who's the them both? Ah, okay. Yes, yes. And so you do this. Yeah, I'm with you. I thought you were saying them both in the fact that you have 2 there, right? Are we going to have to deal with that? Does that 2 need to be Does that need to be changed? Does that square root affect that too, or only the L squared? We could try this. if we needed to, right? It does affect the 2. Yeah. Right now it's like it's under the square root. That means it affects it, right? Like that's what it means to be affected by the square root, is to be under it. Right. If only the L squared was under it or something, right? Yeah, exactly. So then what do we get? Not 2L. I'm with you on the L squared getting square rooted to become L. I'm with you on that part. But, yes, root 2L. Root 2L, okay? Another way to sort of see this, and this is like tough to see at the start, but it is something that like is there, and you can sometimes get lucky by checking for this, because you know them, we love them. Our favorite right angle triangles are 1, 1, and square root of 2. And okay, so this is when these are 45. Yes. Yeah. Ugh. Okay, so these are so like these are almost like the only triangles that we use moving forward, and how things sometimes get like simplified really fast. There's also a few others that we like to use that have like whole numbers. Like for example, I don't know if you've seen this, but something to sort of note is that like 5, 12, and 13 work out to, these are called Pythagorean triplets, that they work out to be the same number. I'm sure you've seen a version of this triangle that works out, right? And you could do a multiple of either one of these. There's also another one like 25 and 15 and 35 or 26 or something like that. I don't know, something weird. But that these triangles will? Oh yeah, for sure, for sure. Yeah. I mean they did here. Look. They did here, look, because anytime that you have something that's the same length, this will be root 2 of that same times that same length. Right? Because look, sorry, go ahead. If I multiply this by A, then it multiplies all of them by A. And the L in this example is A. Right. Yeah. So, but if I multiply any of them by a certain value, then it's just kind of like the same number, but with the value there as well, right? Like, so that's the thing. So the other one that you will almost for sure see, and I'm sorry that we're sort of like doing so much of the version, but I'm trying to give you kind of tools as we go forward. Um, is sorry, 1, root 3, and 2. We like to use those numbers too. That one's a little harder to remember, but the quick. Go ahead. Yeah, yeah, exactly. So just remember this. Like this is something that I don't know why we don't cement this into kids' brains, because it's so easy when they're kids about triangles. The smallest side is opposite the smallest angle. The smallest side is up to the smallest angle. The medium side is up to the medium angle. The biggest side is up to the biggest angle, right? So with a hypotenuse, that's always opposite the 90-degree angle, because that's the biggest angle that you're going to have. That's why the hypotenuse is the biggest side, right? So here, 1 is always going to be the shortest length in both triangles. Okay? 1 is the shortest. That's one of the sort of like facts that you need to remember about these two triangles. 2 is in the hypotenuse. Okay? And there's only one square root. Oh, no, sorry, not 3, but only one square root symbol in the whole thing. Okay? That's enough to remember both triangles actually. Okay? So you know that one of them is the 30-60 triangle, one of them is the 45 triangle. Right? You don't have to remember that really. Okay, anyway, sorry. back to, like those are sort of like big moving forward, but and something that we could have used to sort of sniff out or accelerate this a little bit, or catch even that 2, right? Because that was initially just 2L. So root 2L is a big difference there, right? Okay, so then that means we have to plug that in for our radius, right? That's what we were trying to find, was our distance from A to C, right? And it worked out to be 2L. So why did we want the distance from A to C? To plug it into which formula? Yes. Good. So let's do that. Sorry, I just want to kind of declutter here. Okay. Wait a second. Root 2L. All of it squared or just the L squared? All of it squared. Like no matter what the radius is all of it, right? You don't just sort of like choose some part of it, right? You got to do the whole thing. Okay, so then follow through on the math, right? Remember, the goal is to get the original or compare the numbers at least that you get out front, right? So what number do you get out front here? Final answer? Final answer. Do you know who Regis Philbin is? No. Oh. Regis Philbin is the original host of Who Wants to Be a Millionaire. Do you know that show? What? Oh my god, I'm such a boomer. Alright, never mind. They cancel out. What is it? Did you find the original? Uh-huh. Do you agree with me? Okay. So what did we just show? Yeah. Okay. Now zoom out, right? We got a sort of answer here now. So what are we doing here? They're the same. The force that this thing feels from B is the same as what it feels from C? Yeah. Right? Weird. Right? Why? Why? Yeah, for sure. Yeah. Like, and in fact, remember, distance matters more. Distance is what matters most because it gets squared, right? Okay, so good. If I asked you for the direction of the FG, would you be able to tell me? The net FG. Remember, this is the net FG. If what, sorry? Mm-hmm. Mm-hmm. Oh, wait a second, wait a second. What type of force is it feeling? A push or a pull? Gravity does what? A pull. Gravity doesn't do pushing, right? So it's feeling a pull from both of them. Both of those things are to the right of it, right? So it should be moving to the right here, right? Do you agree? That its net force will be to the right here, towards those objects that are pulling on it? Somewhere to the right. Maybe not perfectly to the right, maybe not like a little bit up, a little bit down, whatever, but at least to the right. Oh, you have to specify direction, yes, but I'm just sort of trying to get your bearing, okay? Okay. What are the two for like what we're doing here is kind of cheap. We're using scalars. These are vectors. Let's make them vectors. What's their direction? Sure. So, we can now say we're on a sort of compass, sure. It doesn't matter, it doesn't matter. That's fine. We could say to the right, like you should be comfortable with both systems, like to the right, up, down, left, right, or east, north, east, south, west, okay? So what about the direction for FAC? That's a little different. I did it terribly, but oh god, let's at least make these quality here. So your angle, if your two sides are the same, your two angles are the same. Which means your two angles are what if you already have a 90? Yeah. So this one here has 45, 45, 45. No, sorry, 45, 45, 90. Sure, sure. Yeah. South, 45 east. Okay. Wait a second. Double check your directions there. West. Which is that west? Which way is A feeling? Put yourself at A. What do you feel? Yeah. Which is what on the compass? Wait a second. Wait a second. Where are you at? Where are you at right now? What city? Okay. What is out east? You don't know? Okay, what's in the Maritimes? Like, what province? New Brunswick. Nova Scotia. Come on, you can't forget our I know there's only like, 100,000 of them, but you can't forget PEI and all those, right? Okay. That's out east. Yeah? What's out west? Have you heard it called out west, like BC? You ever been out west, seen the mountains out west? Right? That's how I remember. That's honestly how I remember. Um, exactly. So that's another one. Like you find one that works that's like funny or weird or about somebody that you know. That's a really good one too, because that's like you're associating it with some actual thing that has a place already in your mind. Never eat soggy waffles. Ours was never eat sour watermelon. Sour watermelon. Which is like okay, like yeah, it's like I don't have like watermelon hanging around all that often that it gets sour, like I guess. So, but it became something that you remember, like just like mitochondria is the powerhouse of the cell, the reason that became a meme is because people just have that like lingering in their mind, like they've heard it in the background so many times, right? Like that's the sort of same sort of thing, right? So, okay, anyway, back to this, your triangle, if you have the two the same length, then your two angles have to be the same, right? And the only way that works is 45. So that's 45. So that's south 45. That's east. And this one is east. They have to be the same direction, right? Because we said they're both going to be pulled to the right, right? So we both could have called them to the right, yeah? Down 45 right. Okay, what do we do about adding well, I kind of gave it away there, but to say FG, that's one force. It may feel it from two things, but it's just one force, right? So it's, well, southeast, that's favoring AC. You're pretending like B isn't there. Remember, they're equal. What? Yes, okay, but look, what you have right now are two vectors. One that looks like this. Let's just say three, you know, I don't want to say big G, but let's just say big K. Is that okay? Let's just say that that number ends up being 3 big K. Okay? And then this one is 3 big K. Right? That's what they both ended up being. And this one was at an angle of 45 degrees. Right? What you're trying to do is you're trying to give me one vector that represents both of these at the same time. The only way we do that is if we add them together. We got to add them together. How do we do that? How do we add vectors together here? Yeah. Another way to think of this is that they're also both going to pull on a rope, right? And they're both pulling with the same strength. Yes. Can I ask you, is it going to be closer to the top or closer to the bottom? Or like the angled one? Or is it going to be right in between? There you go. That's the answer. It's going to be right in between. Yeah. No, I mean, if we both pull with the same strength, then it's going to be kind of like half your angle, half my angle, right? The true best way to do this would be to break these things down into components. So to say 3K, this one is all in the X, right? But then this one kind of has its own triangle that is each of these are the same value because this is 45, right? But they have an X part and a Y part there, right? And so then we would add this 3K to that X, and we would only have that Y, so we would do mostly X, but then we would do a little bit of Y, right? So, but either way, we could still say that it's going to be right in between them. Another thing we could do is the parallelogram method. Remember that with physics? Yes, we can make a parallelogram of the sort of two vectors twice. But once kind of going like down the block and then up the block, and this one goes up the block and then down the block. Do you agree that they're going to get to the same spot? Okay, that's what the parallelogram method is, right? What's nice about this is because they're the same vectors and a lot of the same lengths and a lot of the same angles, and you now have an enclosed 360 total inside angles, like you now know things about four-sided shapes that you can do math with, right? So this vector here, that vector, uh, in our parallelogram. Okay, this is terrible. So actually, I think I have a parallelogram here. Uh, what would you actually what? Um, no, it would be right in between. So it would be half of 45. Yeah, exactly. And its size would be something that we would have to actually do the components for anyway. So we would have to, or we could maybe get away with doing, because look, this is a triangle now that we can do sine law, cosine law, right? Sine law and cosine law are going to show up a lot when we do this, and we have A and B, okay? So something to note here in our parallelogram method, this is A plus B, the one across, okay? And the one diagonal this way, kind of like from opposite corners, is A minus B. Okay? Which is weird, but that's something that's true. But anyway, you can use sine law, cosine law with that triangle there. Okay? Is it confusing? Okay. So can I see? I just want to see. Yeah. Okay. So did a similar sort of thing there. Yeah. So okay. So look at number 3. Number 3 is breaking that thing down into components to get f13x and f13y. So he broke down. So as soon as he saw, like for example, us seeing AC, excuse me, we know for sure that that's going to be a diagonal one. So we could break that up into ACX, ACY, right? And then when we get down the line, when we're going to add a bunch of these individual vectors together, we'll just add all the x's together. We'll add all the y's together, right? So that's what he does right away. He turns 1, 3 into an x and into a y. Okay? And look, actually, the ratios and stuff that he comes up with, you're like, wait, what? What is this 3 over 2 root 2, right? Like, you might be asking that question. Those are our old friends that come up in these triangles here. That's where that's coming from. Is he did the cos of 45. Cos of 45 is 1 over root 2 from this triangle, right? Cos of 45 is adjacent over hypotenuse, right? So that's where the 1 over root 2's come from. And the 3's, sometimes you get root 3 or whatever, right? Okay. So, yeah, so he just broke down immediately all of the x's, all of the y's. So we did all the x's, added them together. And then I think that was it, right? Oh, this was, Oh yeah, this is talking about mass M, right? Yeah, exactly. Okay. So yeah, it was 1, 2 plus that, and then there was F1y. Where did F1y come in? Oh, he did do, okay, with where it says Pythagorean, you see that? Like on 6, number 6? That's where he brought in F13y, right? And the result of 1, 2 and 1, 3x up above, right? Because that's now a right angle triangle. And that's going to be your, so all he did was broke up into components right away, kind of as he was going along, and then at the end just added up all the x's, added up all the y's. There was only one y, so he just used it, and then did a Pythagorean theorem with that, did a SOHCAHTOA with that to find the angle, and we're good, right? You'll always be able to do that too. Like that's what's nice about this method too. If if sometimes you're just given these numbers, then you can just use sine law, cosine law instead of having to break it down. But generally, if you're going somewhere on your way, don't use sine law, cosine law. Just break down into components. Okay. Yeah, so break down to components is so big here, and then add them up at the end. Exactly. Yeah, and then we would have added only AB because AB is only in the x. And we would have added that to the little x component that was coming from AC, and then we would have used the y from AC. Yeah, sorry, I probably interrupted you, but I sounded like that was what you were about to say. Yeah, exactly. Awesome. Okay, cool. And you'll always be able to do that, turn that into a future Pythagorean theorem with both sums, right? Like that is, if anything, that is the theme of this year is break down into components, sum up all the x's, sum up all the y's, you'll be able to add them together. Anytime you're dealing with vectors, that's going to be something you do, okay? So kind of get, and breaking them down to sum them up, you're kind of like doing the backwards, of each other, right? Like on the way there. Breaking them down is the opposite of that. So you should always break down, you should always kind of like add them up like that. Okay? Okay, sorry, we're sort of like, slowly working our way, but yeah. So I actually have to get running here, but um, is it okay if we sort of leave it there? Do you feel a lot better with some of this gravity stuff? I was trying to sort of hit on some other types of questions that you might see um, along the way. Mm-hmm.